Hello fellow problem solvers, so they're going to be doing a problem from the Junior Balkan Math Olympiad 2017, problem number 3. This is a special problem to my heart because it was proposed by me. At the end of the video, I'll tell you exactly how I came up with the problem. So, I'd invite you to try this nice geometry problem out for a minimum of 15-30 minutes, ideally an hour to an hour and a half, not more than 3.5 hours. If you'd like to go along with us, give it a go for the next, 15 minutes. You draw the diagram, put your first ideas out on paper, and now let's begin. So, whoa, it's a mouthful. I need to act surprised even though I made the problem. Oh my god, it's such a mouthful. Look how many points we have. How are we ever going to do this? And the answer is step by step by step. So now, what do? ABC is an acute triangle with, okay, these are different, and circumcircles this, okay, circumcenters those. So let's draw a bad diagram at the beginning, just to see like what's happening. Okay, maybe not a bad diagram, but just like a decent one where we don't put way too much effort into it. So, okay, O is here. I'll have the midpoint of BC. Remember that. So that's like boom, here 90. What's that midpoint? It's M. And I'll have A over here. Kaboom, this is different from this. And a point here, D, such that this is perpendicular to this. This is the circumcircle. And now let's see what we have. T is a point such that BDCT is a parallelogram. I'm just like recalling now how it is I made this, this problem. So that is really just a reflection of D with respect to M. Oh, I can see now why it seems so like, ooh, scary. And so we have this is D. It's here, a reflection here. Okay. What else do we have? And Q is this point such that BQM is BCA and CQM. So BQM is BCA. So that's a point, like, where do we draw this point is the question now. Well, maybe, before we draw the point, let's just see, like, what do we have here? What do we have for this? This is 90 minus gamma. So this is 90 minus gamma. And then this thing right here is 90 minus gamma because this is gamma. This is going to be 2 gamma minus 90. And with that, this is also going to be 90 minus beta. Like we know something about points T, and why am I looking at things for points T? I'm looking at them because Q you can look at, like we have the circumcircle of ETQ. E, where's E? What's the point E? How I missed E? Oh yes, AO meets the circumcircle of ABC. What did I do to these kids? I'm just looking at this now. Meets it here, and then ETQ meets it at X. Oh my god, what did I ever do to these kids? So let's wow, actually, like now I'm recalling the problem as I'm working through this of how everything went through. So maybe let's add Q later. It seems like E is an easier add than Q. Let's see what happens. We'll get ET and Q, that circumcircle intersect this one again at X. So let's maybe work at it backwards, see sort of where is this point Q, like what is this point Q all about? So what do we have? I just remembered like my entire idea for this problem and how I constructed it. So we have this angle right here is equal to what? Well, it's equal to this angle, which is equal to 90 minus gamma. And similarly, this is 90 minus beta. So we have E and T are symmetric to one another, right? With respect to the line BC. So CE is CT, BT is BE. This is a kite, I think is the terminology. So we have TE is perpendicular to BC. With this, I invite you to pause for another 10 minutes, maybe 10 minutes. If you're new to geometry, pause for 30 minutes and try to push the problem further. And here's the next step. So what do we have? We have this at 90. And we can look at the problem two ways. Like the biggest sort of question is, what is this point Q? What is it doing? And that is just like the question of the day here. So we need to see, like, when we intersect AM, here we'll get a point X, like that's going to be X. But this Q is something that we just don't have anything holding it together. Like it's just, you could even think of Q as being at the end constructed. You could have, like, say this is the construction of Q, X is like just like AM intersect this, and then prove that Q is also on this circumcircle, right? That could also be a way to think about the point Q. So how are we going to look at this point Q now? So let me just now construct it. So we have such that this angle is gamma and CQM is beta. So if I make it around here, Q, such that this angle right here, BQM is gamma and CQM is beta. These are not collinear because Q is symmetric with respect to B and C. With respect to B and C, and A being like some sort of axis of symmetry. But it's like symmetric with respect to B and C, so these can't be collinear. Now, if this is gamma beta, so in total it is alpha plus, it's 180 minus alpha. On the other hand, for this point X, we will also have it is 180 minus alpha. You know, there could be some, like, so when we reflect Q here, it's also on, when we reflect Q with respect to BC, it should be on the circumcircle of ABC. And with this, I invite you to pause for another 10, 15 minutes and try to push the problem further. And here's the next sort of step. The next step says, wait a second. Looking at the problem backwards, as we sometimes do, you say, okay, wait, if I reflect a reflection of Q with respect to BC is on the circumcircle. Reflection of T with respect to what's called BC is on the circumcircle. Q, and say this other reflection with respect to BC. Right, I'm having a point here, Q, and then I have the point T. I have this is a reflection. What happens also when I reflect this point? Well, the midline, say this is called this Q prime, this is E. What is the, what's it called, the side bisector of QQ prime? It's BC. Of TE, it's BC. So if I connect T and Q, take their side bisector intersected with BC, I'll get this is equal to this because it's a side bisector. I'll get this is equal to this because it's on this side bisector. And also this is equal to this. So I'll have this is the circumcenter of QQ prime ET, which means these 4 points are concyclic. So this point X, it has to have these two things hold for it, right? So it has to have, so now we have, once we intersect AM, if we're going to like label this as X prime, like intersecting it with respect to the circumcircle, we'll get this is beta and this is gamma. And now can we make an argument that these 2 points are reflections of one another? Because if we can, then we've proved that X prime is in fact X. That is one way of going about it. So, and how can we actually go ahead and prove this? We don't really have the angles, so it's a difficult task to actually, I mean, we have these angles, and I think without using any trigonometry, it's a bit of a difficult job to actually go ahead and prove this. Maybe if I reflect this here, if I actually reflect now X prime to Q prime, then I would have these are concyclic, and so like the points x prime, q prime. Now, when I reflect x prime and I have it here, then I'll have MC q prime are concyclic, B M q prime are concyclic, and from there it follows that like if q and q prime aren't the same, because that is the only like q prime and m can't be the same, then B and C lie on the circumcircle around q prime, which is impossible because B, M, C lie on the line. So that means Q and Q prime have to be the same. That finishes up the problem like that. But a simpler way to also finish the problem is just to, instead of labeling, actually is that, I think that is perhaps the simplest way to finish the problem. If I reflect Q with respect to BC, I have, it's going to be, say, a point Q prime. Now I know this point, Q prime, is on the, what's it called, the circumcircle of ABC, because this angle is 180 minus alpha. But I also know this angle here is equal to this one, which is beta. And this angle right here is equal to gamma. MQ prime B is gamma. And I know these are concyclic because of the argument that we had here. So that's why I know these 4 points are concyclic. And so, what's it called? Now, because the angle MQ prime C is AQ prime C, because AQ prime C is ABC, is beta, that means that AMQ prime are collinear. And this finishes up the problem. Like, you need to redefine the point in some way. The reason you do that is because this intersection right here, when you have it in the beginning, it's nasty. It doesn't, it's just, yeah. I don't want to deal with that. So that is why you have to do this sort of intersection kind of deal, like redefining a point. Now, how did I construct this problem? I'll tell you that story, because this was not the intended solution. This is sort of maybe the most logical step-by-step solution. I proposed a couple of geometry problems to JBMO for this year. And this one was sort of it was really like, I know what holds for a point. Let me reflect. Let me just put something together. This was not, in my opinion, my most beautiful geometry proposal, but it's the one that passed. And that's sometimes strange, like how that happens. But how I constructed this was, let me do a better diagram here. So the diagram I had here was this point Q. I had did a little video on this, and it's a point with a lot of characteristics. Like if I take the point where I take AM and I take H, I put a perpendicular to AM, call that point Q. This has a lot of characteristics. One of the characteristics was that this BQ over CQ is equal to AB over AC. And this is also 180 minus alpha. So when I reflect it here to point Q prime, I'll get it's on the circumcircle. I also know that H, the orthocenter reflected over BC, is on the circumcircle of ABC. So that means that these 4 points are concyclic. Okay, so that's my starting thing. How I looking at the problem. Okay, these 4 points are concyclic. Now, this is also why I'm not a huge fan of this problem. And now I'm like, okay, how can I hide something here? Because this is the kind of trivial-ish, try to prove this. Like if you know everything about the point Q, you'll just finish right away. So one way is to say, I know for this point Q, I have BQ prime, this point Q prime, BQ prime over CQ prime is AB over AC. When I intersect AM here with a circumcircle, I'll get this over this, is this over this, i.e. this point, call it X, this is equal to this. CX is BQ prime. And also this is equal to this. So I know these facts, and I'm thinking to myself, okay, what happens if I take, so what happens when I take the reflection of A on the circumcircle here? I also know that Q prime M and this point, call it, say, A prime, that these 4 will be collinear. And then I thought, wait a second. I need this point right here. I need H. Let me define everything. Let me define Q, H, and D with respect to this triangle, A prime, BC. And let me define them with respect to that. And that will hide the fact that this is the orthocenter, this is the mysterious point Q, as I call it, or the chef's point Q. And that is how I'll hide the fact that this is Q, this is H, and that these are like connected in some way. And after that, it's just a matter of, okay, how do I hide it better? I can say, okay, I can reflect, when I reflect H here, I know this is perpendicular to this. A prime, call this now D prime, is perpendicular to BC. D prime is D. And then I'll have H as D prime reflected over here. I'll just say parallelogram. Boom, you have the point, what was it, T. And now when I have T, okay, how do I get D? I'll just get it as AO, intersection here, sort of hide the fact that these are symmetric to one another. You have a point there, you can get a point or two there if I do that, and that can make it a nice geometry problem. So I hide this point. What am I now going to do with Q? Q I'll just define with respect to these angles because it's a unique point with those angles. Right? So that's how I'll hide Q, and Q will be the thing I'll hide. And I was very, very into this point back in 2017 when I made the problem. So that's how I'll hide Q. Oh, and then what I'll have to prove is that this, and this are concyclic when I intersect this with the circumcircle again. And that's how the problem came about. Legit, and it took me less than an hour to come up with this. I was trying to come up with cool problems, and I came up with this. But there was a problem I remember really, really working hard on, trying to like make it good, make it interesting, appealing, and then this thing passed. I was like, okay, okay, it's a problem at the JBMO. I'm satisfied. Even though I was like, I had a better problem. And I was actually surprised to have it at a number 3. But I guess the idea that you're just like reflecting this, that I hit the points well enough that the jury thought to say, okay, let's put it as number 3. It's a harder geometry problem. And that's the story behind how I made this problem. And I'm kind of, I feel happy about it now, like the way it looks here. And the solution I recommended was, let's reflect A over the side bisector of BC. And then from there, we will prove like that Q is in fact collinear with D, because then when we reflect it, we'll have this angle as beta. And then from there on, it's not more interesting per se. I would still need to then outdefine Q as, let's put a point on this and M such that this angle is beta, and then I have this squared is this times this. There's also this squared, so this is gamma, so that is the point Q. Because the big question is like, how do you construct Q in these types of problems? Like, how do you construct them? And that's how I construct Q. And then this point E is just perpendicular. This point T is also, because this is what's it called, just by angle chasing, this O and this point are collinear. So when I reflect this to T, I have the orthocenter by a lemma I know, and I write that down, and then I know these 3 are collinear. I know what Q is. And then this intersection right here is, and then me prove A, this, and this are concyclic. It's the same as me proving when I intersect this here, that I'll get this is equal to this, or these 2 are parallel to BC. I think that's the way to go about it. And then this, then what this is equal to this, right? How do I prove that? I honestly forgot, but I think this was like where my idea for a solution was headed, and why I thought the problem like had some coolness factor to it. And this finishes up the problem, and as always, Thanks for problem solving.